making use of the 3D printing technology. So definitely it will enable to solve complex surgeries. So then the conventional surgical procedures, wherever you have a difficulty, so this technology is always be there to solve those complex situations. So then we will discuss that how it has been helped in one of the dental case studies, excuse me, to place the implant. And the third case study, third, fourth, fifth, sixth. So these are predominantly on the oral maxillofacial case studies. So that is how 3D printing helpful for either reconstructive surgeries in oral maxillofacial department, like say how this technology helpful for reconstructing the mandibular, that is lower jaw of the say the mandible part, how it has been reconstructed by using by this by helping the patient to reconstruct the bone with the aid of 3D printing technology. So how it has been helped the technology, 3D printing technology, in solving those kind of complex surgeries. So then we have another case study. So this is a cancer patient. So again, so we need to remove the bone from the cancer patient. Then how 3D printing helpful for making use of this technology for performing that say surgery for the cancer patient, how it has been helped. And the fifth case study, so this is one of the most complex case studies. Normally the oral maxillofacial surgeon come across is a TMJ ankylosis, that is temporomandibular joint ankylosis. So that is the joint which joins the lower jaw and upper jaw. So that joint, so one of the patient by birth she had a got fusion of that joint. So how this technology helpful for say reconstructing that joint freshly. Say that is about the fifth case, and how the 3D printing technology, especially metal 3D printing, helpful for say fabricating, designing, fabricating, and developing this say TMJ joint. So that is what the fifth case study. And the sixth case study, again a metal 3D printing technology helpful for designing and fabricating the indigenous implant for a patient specific or patient matched for. This is one of the accident case. So he needs say the nerve relieving as well as five teeth he lost, and along with the bone, the upper jaw. So he got damaged in a accident. So how 3D printing helpful in this direction. And lastly, of course, the argon printing. So I am not an expert in argon printing, but definitely it leads to an argon printing. And we'll see the state of art of argon printing by using 3D printing. So though this is early, too early, or it is a future technology, there will be several challenges that the Argon printing is in the recent times, or its very beginning stage, how these challenges can be overcome. So that is the last agenda point of my presentation. So this is the outline of my presentation. Maybe the next 1.5 hours or so, we are going to discuss this. And let us quickly introduce this, say, medical 3D printing practice. So I hope the previous speakers might have enlightened you on the several aspects of 3D printing. So the basics or the applications and other. Say, when you come to application of 3D printing in medicine, it should come from the digital data. So it is none other than in medicine. So we need to start with medical image processing. So then you either take an X-ray. So the X-ray scenario also, it has been now the scenario of digital X-ray has come, and further you have computed tomography or CT for, say, diagnosing the bony kind of a tissues. And you have another scanning modality, that is MRI, that is magnetic resonance imaging, where your tissue of study is the soft tissue. Then you may be advised to undergo an MRI examination. So the journey starts with either a CT or a MRI scan data. So from the patient, it has been collected. So that's going to be the start point of your, say, medical 3D printing journey. So we need to start with the digital data that has been collected from the CT, MRI, or even it could be a PET, or even it could be any other angiogram data. But it should come in a digital form, and that it should come in a DICOM format. That is one of the formats that any scanner it supports. So any medical diagnostic modality will support that. So just you get the DICOM images from any one of these sources. So then your DICOM image, basically it consists of a two-dimensional cross section. So these two-dimensional cross sections, further it has been reconstructed into a three-dimensional, say, model. So that three-dimensional model, say, how you are going to reconstruct. So you have several medical image processing software tools to do this job. And this will be, say, for example, you have taken a patient, COVID patient, CT scan, the chest CT of a COVID patient, to know the level of infection that he or she is having. So then during your CT data, say, collection, so then you may be also collected the other tissues, like you might have. So because you have an adjacent tissues, or like you have the ribs and you have the spine, and you have the lungs. But at this point of time, your region of interest or organ of interest is lungs. So then you can, say, segment other tissues, or you may be interested for only the lungs as an organ. That is the organ of study for the COVID patient, say, requirement. So in that case, where you need to, say, say, process these images, so to pick the region of interest as a lungs, and you save that data into an STL file or an AMF or a 3MF or .obj, or whichever file format your 3D printer is supporting. So then typically it will be an STL file. But even it could be other file formats in the recent times. The printers can understand and can take up the input data. And then once you say generated your data, which is understood by the um, 3D printer, so then next you may take this data back and forth to a CAD system, um, or even you do simulate a surgery that you have designed certain implant or certain joint for a pelvic joint. Then you need to say simulate that before you go to the actual real-time surgery. So then these softwares will allow you to do simulate the surgery. So as for your um, patient-specific design, based on the patient condition, this data has been captured, and further you have designed a customized implant for the patient-specific requirement. And you can even simulate this surgery, or even you can make a 3D model, computer model, or further, depending upon your application. So your orthopedician, say, you have designed a femur implant for the orthopedician. So we need to check for the failure of that implant before you implant it into the patient body. So then you do FEA analysis, or sometimes you do a CFD analysis for the cardiac applications or a neuro applications. So then you may even do a sort of CFD analysis. So which your data has been captured from the patient, and it has been say further say done through your say any one of these tools. And even further, you want to realize a physical model which you have been captured from the human anatomy. So then very well your 3D printing technology is helpful to physically fabricate your model and then use it for your application. Maybe um, just this is a diagnostic model, or just this is a pre-planning model, or to rehearsal the surgery you can make use of it, or you go to the next level of application to design an implant, or to design a prosthetic, or to design a device for your surgical aid for your surgeon. So that is also very well you can do it based on your say the requirement. Then you can do accordingly. And sometimes you do a design validation. So the design validation should be also done. So then what are the various data processing softwares or the medical image processing softwares that you come across, or you can make use of several software tools that are available. Say some of them which are listed here are the commercial softwares, like which we have at our place. We have a mimic software from Materialize, so you can make use of that software. Or otherwise you may have other softwares like Dolphin 3D Surgery or 3D Doctor, Simpleware, and several commercial softwares. And now if you are looking for some open source software for doing say the basic preliminary operations, like converting your DICOM images into an STL file, so that is very much needed for your 3D printing process. So then you can make use of this 3D slicer software, which you could able to say convert your DICOM images into a printer recognizable formats, and further so you can do a bit of segmentation to a segmentation process and region growing process, and certain tools are so by making use of those tools, even you can do some extent this modeling also. So then you can make use of your the tools that is based on your budget or based on your facility you have. So then you can make use of any one of these medical image processing software tool to process your medical images and further ready for the 3D printing uh, process. So yeah, then you may wonder, say, why you need to have a physical model, though you have a virtual model, so which it has been gathered from the patient data, and further it has been, say reconstructed in a computer, and we are using for the simulation purpose, virtual simulation. But still, why we need to have a physical model? So definitely, a physical model is a physical model. You have a physical feel and say feel, touch and feel kind of thing. So why you need such a touch and feel? So definitely, if you see a, a oral maxillofacial reconstructive surgery for them, say one patient who needs badly an implant. So this implant at the region of zygomatic region, and it also covers, say, um, um, the orbital rim portion. So where not only a oral maxillofacial surgeon is going to be in this surgery, but even an ophthalmologist is also the part of the surgery. So what I am trying to say, even you have other, say, the surgical teams consists of different departments, and they need to work together. And then once you have a physical model, and then you can very well communicate to your co-surgeon or to the patient, you can communicate better, so what you are going to do. And and not only that, even you can correctly place the eyeball for an ophthalmologist, or even for the oral maxillofacial surgeon. So you can even very well, say, design this implant at the zygomatic region. So you have such a wonderful opportunity in terms of physical models for, it need not be a oral maxillofacial. It could be a pelvic joint or a femur, or even it could be a skull region, or a, say, mandibular portion, or mandible maxilla portion, or everywhere. So any human anatomy, so that has been mimicked or biomimicked as for the patient, say, data. So then you can make use of those models. Once you have the physical models, so you can communicate that the better surgical team communication will happen between the various say departments of your surgical departments. And even you can educate the patient, and you it will assist the surgeon to diagnose and surgical planning. So then what are all the tools or the surgical devices, so they need to carry, or they can very well plan the surgery before they enter into the, say, operation theater. Even they can take these models into the operation theater, and they can intraoperatively work on these, say, models. So even it will also allows to do a rehearsal of the surgery and to do the simulation of the surgery. And at the end of the day, the surgeon may come out with the the best surgical procedure never had been. It may even lead to an innovative surgical procedure at the end of the day, because of these physical models which they derived from the patient data. So that is the biggest advantage. And you're going to customize as for the patient requirement your implants or your prosthetics, so that is exactly fitting to the patient need. Otherwise, and conventionally they take a standard sized implants and they are trying to fitting it. But here you don't have such a, say, a rude procedure, or it's going to be an exact procedure. It's going to be happen by making use of these models. And even you can create and customized prosthetics. That's what, like, where you can, that is patient You can customize as for the patient. Say the prosthetic maybe, and a person lost his say the limb, so you can design an artificial limb, or you can design an artificial, say, nose, ear, or whatever it is. Like, say, you can even better customize these prosthetics, so as for the patient condition or the requirement. And you can accurately place the implant, so that is the another advantage to have this kind of say the physical models. So these physical models, so when say you use a 3D printing process, so then we need to start a CT or MRI, say, with your region of interest. So you are targeting to a particular anatomy of the patient, which then you ask the patient to undergo an examination of these data or image acquiring system, and then you get those images, and then you can reconstruct. Just now we have discussed how you are going to reconstruct these images. So once you reconstruct these images, so now you can link your standard 3D printing process. What is that standard 3D printing process steps involved? I hope you are very much familiar by this time. So then you use that, say, the process plan that you come across in a typical 3D printing process, maybe by fixing the orientation and by generating the supports, and then by generating the say the cross sectional data or the layers. And once you generate that the cross sectional data through a slicing algorithm, and you send that codes to the machine. So as we know that inside the machine, so without writing any code, just with the data that has been supplied to the software, and it has been generated automatically these instructions to the machine. So based on that instructions, uh, uh, say whatever may be the part that you have supplied here, like a skull, so then it is exactly going to replicate a physical realization has been happened in the, say, machine. So the physical fabrication has been done layer by layer here. So then once you complete that all layers, then finally you end up with the model. So then you use that model, either you use that model as just for say study the or diagnostic purpose or planning purpose or implantation purpose or prosthetics design, or some device or some template you want to design, or some guide you want to design for assisting the surgery based on this patient data. So then you can, say, perform. So now if you talk about the argon printing, so then what is going to be the material? So that's only the difference, but 3D printing process remains same, whether you use a synthetic material, so like, say, a plastic material like ABS, or if it is a metal, maybe steel, cobalt, chrome, titanium, or any other metal, or ceramics, so, or composites can be used. But if you talk about the argon printing, so your material is a natural material, or even it is nothing but a living cells, so that has been taken from the patient own patient body, and it has been, say, printed, or it has been, say, grown into an incubator, and doing a cell cultivation, and finally it has been, say, sent to the say machine. And then once you have that say now you have printed the argon, instead you have printed a model in earlier case, but now, but I hope I'm not expert in this, maybe other speakers might have enlightened you about the argon thing. But how it is getting the 3D printed connected Means like you have the material is totally different here rather than a synthetic or a man-made material. You take the natural material, a living cell from the patient, one patient. So that's it. And it may work for your say printing of this, but there will be several challenges to attain the properties that the natural bone or the native organ that you are targeting to replace or you are targeting to repair that organ. So it matters, right? So then how you are going to attain these characteristics or these properties that the native or the original organ or the original tissue that the patient and how it is getting matched. So that's the matter here, right? So anyway, so this is the general procedure you come across for any medical 3D printing process. So then you may have several applications of this 3D printing in medicine. So right from the orthopedic applications to so through my 6 case studies, I'm going to cover 3 areas, that is dental implantation, cranioplasty surgeries, and maxillofacial say surgeries. So these are the say the case studies I'm going to discuss with our personal experience on these 3 areas with 3D printing. And it can be used as a biomedical devices, this practice, and biosensors can be developed through the 3D printing technology, and biomems devices can be developed, and microfluidic devices for bioseparation and bioprocessing so can be used, and augmented tangible molecular models for research and education purpose means so for a anatomy student for a medical side or uh, a DNA should be say studied or say you can even make say then what is the advantage of printing these models for these kind of studies or this kind of research education. So definitely you need not worry about preserving them into conventionally they do with such kind of preservation in a liquid and maintenance is very tough to maintain that cadaver bones or a dry bones. But here you can very well print them and then you can make use of these models for those purposes. So and anyway, so we'll come to our case studies. Say the first case study here I'm going to discuss is a cranioplasty. Means so this is say how we have used the medical image processing tools and 3D printing together to model and analyze this cranial implant for a patient matched application. Say so this is the cranium bone, which I already say said you regarding the cranial bone is the bone is a part of the skull bone which protects the brain. And the challenge here is so these are the images. It has been imported into the software called Mimics. For that matter, you can import to any of the medical image processing softwares that you come across which you are having, or you can use a open source softwares to do this job. So you import these images into this software, and then you can say reconstruct the from the images to the skull and this skull part, and where you are looking to design an implant for this say the cranial region. So the biggest challenge here is like say the thickness of the skull bone is not uniform. So we need to say customize, we need to design an implant which should fit to this. The fitment is very important. Why? Because so we have a cerebrospinal fluid, so that fluid will be generated in the brain and it will be pumping or it will be supplying through the spine, so to the spine, brain to spine, so it will be supplying. So then you need to carefully design this implant. The fitment is very important here. So then how do you ensure that you have a better fitment of this implant? So then initially we need to take a several measurements of this, and further we need to say design an implant, and for that you have several tools here to do that. And initially you do this the segmentation part by supplying the threshold values that you are looking at the bone will be having. So again, bone, you have a different bones, like you have a trabecular bone and you have say cortical bone, and then based on the region and where you supply that the threshold values, so that's basically based on the density of the tissue, so that is getting say captured, or that is getting reconstructed here, and then now you design an implant so that this missed portion of this cranial, so that will be done by making use of the other software called thematic. So then anyway you use certain software tools to reconstruct, or rather than to design your implant, so the cranial implant, and further you convert that as an STL file and you print them on a 3D printer. So then we tried in several, say say 1 2 3, like we tried to check that the fitment is proper. So this implant versus the native skull of the patient. So then the native skull of the patient, which we had this say reconstructed skull, and it has been printed separately, and this implant has been printed separately and tested for the fitment. And further, so this we have published in one of the journals. And further it should be, say, what you call, so not all the times you have an opportunity to say use a mirror command to copy the defect side to the say survive it to the defect side, but where sometimes we need to develop our own algorithms. So we developed a nerves-based reconstruction algorithm to that is so which is beyond the midline defect area. So where we we have developed that algorithm, and then we integrated and we say simulated that reconstructed, say, implant for the, say, fixation points. So how many fixation points we need to, so ultimately your implant is getting fixed onto the skull of the patient. So then how many fixation points and the location of the fixation points matters a lot regarding the say your the pressure of that body fluid is exerting onto the implant. So it should be uniform. Then ensure that your say the fixation points, the location of the fixation points, and the number of fixation points, so should allow us to have a uniform pressure has been exerted. So that's what we have done, simulation of this. And further we have checked for the printing of this implant. So we we check for the biocompatible materials that you can print them out. So through the polymer, say group peak was considered polyether ether ketone and polymethyl methacrylate PMMA, and from the metal side, so titanium 64 has been considered for the study for the material study, and then further we have studied the equivalent stresses, and then ultimately we need to say come out with the best material and the best say design to fitment, and analyzed all these things, and further we have published this in one of the repeated journals. So if you are interested to know about further, you can refer to this journal. And ultimately our aim is to say say print this implant, so which is specific to the patient, means none other than this technology will give this kind of solution. Why? Because so you have a totally um, say a sandwich kind of a structure here. Means, like, say, if you closely observe your skull bone, is not a uniform cross section across. So you have the say the inner bone maybe around zero point 0.7, 0.8 mm thickness, the outer bone maybe around zero point 0.5, 0.4 mm thickness, and in between you have a porous kind of a bone. So the then how do you get matched this structure with the native skull bone? That is the challenging one. And then we have an opportunity here to design a lattice-based structures to do this job. And then further, it has been say analyzed for say we have done a homogeneous kind of scaffold-based designing for this implant, and basically it's a unit cell based algorithm, and this is a meshless approach. So if you want to know about further about this algorithm, and you can refer this article. So in this way, where your 3D printing technology helpful to make a customized or biomimic the native structure of the patient exactly it is say matching. Otherwise, so it may not be correctly biomimicked, exactly biomimicked, not through the conventional manufacturing or conventional surgical procedures normally they do. But this is an opportunity for them to explore these kind of benefits. And the second case is a dental case. So in this dental case study, so how this technology helpful for fixing an implant, placing an implant here. So the biggest challenge for a dentist, say, it, uh, he is a patient who is a 19-year-old boy and who needs two implants at these smaller places which the teeth got missed. And standard conventional procedure, they will take an impression from the mouth, from POP kind of a plaster of Paris kind of material. They will take an impression from the mouth, and then uh, based on that, they perform the surgery. But here, the biggest challenge for the a surgeon or the dentist is, say, you will be having this inferior alveolar nerve. So this inferior alveolar nerve, uh, anyway you are not able to get the information about this nerve. Why? Because through the impression technique, so you could be able to get only the outer surface of the jawbone, but which he may not be knowing about the information about this nerve. Because of that, he may under drill or he may over drill, and if he over drills, and then there will be a chance then he will damage this nerve. So then you have an opportunity here through 3D printing. So then you can print this model, and then they can rehearsal the surgery based on the model that it has been captured from the patient, and then you give this model and sit with him and let him do a rehearsal, and then come out with the customized implant, rather than taking a standard sized implants and trying to fixing it. And basically they do a trial and error or some guess game. But here you can have an opportunity to exactly say say design fabricate the patient specific implant here to fix it. Say you give this model and sit with the say dentist to let him rehearsal the surgery, and let him come out with the design, say for the implant, like say what is the diameter of the drill is going to use to fix the implants, and then what is the orientation, and what is the say the depth that he or she needs to drill a hole to fix that implant. So then all that will be done on this model. The once he done that, and then finally he goes to the operation theater, and then you can fix that implant as per the design and the condition that the patient. So it has been done, and it has been say directly implanted during the surgery. So how this 3D printing helpful for fixing this placement, placing and as well as designing this implant to the patient required or specific requirement. So this is the dental case study, and the third case study is a mandibular distraction osteogenesis. It is a reconstructive surgery, so the bone reconstructive surgery. So that is on the say the lower jaw of the patient, that is mandibular, and distraction. Um, so there is a device called a distractor to say to guide the bone growth. Normally, they use this surgical procedure called distraction osteogenesis. They cut the bone and they leave the bone, and then the bone will have the bone growth. So then that growth will be so guided by this distractor device, and then. But how 3D printing technology is helpful for this distraction osteogenesis procedure or this surgical procedure. So then she is 8 year old girl. So she needs um, say, which you can see by birth she had the deformity like this, the abnormal growth of the lower jaw. So it has you can see the facial deformity of the say this girl. So then which we need to say perform a bone reconstructive surgery to ensure that she come out with the see the symmetric look of the facial region. And because of this defect, even she could not able to open her mouth. In a normal opening is 4 to 5 centimeters, so she could not able to do that. And this is the another view where you can see the deformity. But again, we need to start with taking the CT data of the patient, and further it has been reconstructed in the software, and then it has been say um, printed these models by using 3D printing technology. But anyway, before that, what we need to do is so we need to say this device I'm talking about. So this device, so you have a screw kind of a device here. So he or she can rotate the screw, and basically what they do is so they cut the bone and they leave the bone, and the bone will have its natural growth. And again, that growth rate depends on the age, gender, and other factors. So based on this, and you have a device called a distractor where they are going to fix this maybe through external or through internal. So it is getting this is the internal mandibular distraction, but even it could be an external say um, distracting also can be done. So based on the patient condition, so how much revolutions, so it is going to advance, and how it is getting, that sort of things can be done by taking these models. So you already fabricated this model through 3D printing technology. So then you sit with the surgeon, and then they can do that calculations. So which it should be twisted, so how much it should be twisted. And if you see the Ramus height of the survived one is this much height, but whereas if you see the defect one is much shorter, and which we need to stretch this Ramus Ramus height should match with this survived side, and those say how much it should be lengthened, and how much it should be twisted. So all that will be calculated based on this model that you have supplied to the say doctor. And then once you they do that, and then they will come out with that distractor, and then they will use this during the surgery, and which you can see this is the before the surgery. The how transformation it has been happened right now. You can see that there's a distractor here, and now you can see there will be certainly an improvement, but you may get doubt why still there is some abnormality. Yes, means if you see, the bone growth will be there up to teenage, and it has been overcorrected as of now. So why? Because she is only 8 9 year old, and once she turns into say 18 19, and it will be corrected finally. So in this way, how your 3D printing uh, helpful for designing these distractors and further say calculating those say vector calculations for the patient based on the patient condition. So all this will be done through the 3D printed uh, models. So, and the next part of the case study, this the fourth case study, is emboloplastic fibrom of mandible or the cancerous bone reconstruction. So, so in this case study, so it has been use this technology for a cancer patient. So the cancer patient who needs to be taken this jaw, totally it should be removed. Why? Because of this, the the tobacco products, then it has been affected by the cancer, and which we need to know way to remove this jaw, and we have to remove this jaw, and this should be so once you remove that jar and then that portion, and then how you are going to design an implant for that portion where you have removed it. So that will be, so you can do it that designing in the software like Thematic, and you can say say make use of the survived say side to the defect side. So you can copy it from the mirroring command, and then so further you can print them, and then you can say let them do a rehearsal here, like how much portion and where they need to cut. So at that region, the cancer or the tumor region, like where it should be removed it. And once you remove it, and we need to design an implant. So that implant is say based on your say his anatomy, and which it should fit, and we need to provide a nerve relieving capability. It means that alveolar inferior nerve will be say starting from this condyle portion, and we need to provide a nerve relieving here to go this, and again it should come from the other side of the condyle portion. So then all that you can very well design this for lightweighted things, and which we have come out with the lattice based design. So the lattice-based design serves two purposes. One will be a lightweighting, so another will be the osteo integration with the bone to the implant. So this will say help the patient, or even the outcome of the surgery is a better outcome of the surgery. So otherwise, what they do a bone grafting technique. So they will take a bone from the patient fibula bone, and they are trying to fitting it, but that may say may not say forming a 4 foot fit, or you never say they never graft the bone. So such a free form and such a say this kind of structure. So they never it never happened. So then which because of this technology, which you could be able to do that, and then they can make use of these models for planning this kind of plates normally conventionally. You may get doubts, sir, you have already designed an implant, then still why you want to go with the conventional method? Yes, actually this was our first attempt to implant it, but we could not succeed it. Why? Because we need to take several say clearances, ethical clearances, and other approvals to implant it. But you can take an say consent from the patient, declaration from the patient, but that won't uh, say sufficient, but which we need to have a certain other formalities and certain other things. But then where we stuck up, um, but we have succeeded in the subsequent say attempts. But anyway, what we have done at this point of time, so they are able to make use of these models for say bending these plates onto the patient specific things, and they have done the say they have done the bone grafting ultimately. Why? Because we could not able to implant it into the patient body, but they have used a conventional thing here to uh, do that. But this is the one after the post-operative things. But still, it was not a successful surgery. They again came to us saying that say it was not successful, the conventional method. So can we even help us to perform the surgery? Then actually we had succeeded in other attempt, and then anyway we have designed the implant for this patient condition and patient specific implant. And then that's what actually what I'm trying to say here is like you have any difficulty in the conventional surgical procedures, so definitely it's going to be the 3D printing will give a solution, better solution if you have difficulties in performing the conventional surgical procedures which you come across. And the next case study, we are succeeded in placing the implant here. This in this case, this is a this is going to be the very complex surgery for a oral maxillofacial surgeon. So this is a temporomandibular joint ankylosis, TMJ ankylosis. So you can see this patient, she had a birth problem of fused this joint here, the lower jaw, upper jaw. So you have a free joint here. So the articulation will be done easily, and normal opening, normal say biting and normal chewing will be done. So the normal opening is 5 to 6 centimeters. So but because one joint got constrained or fused, but even she could not able to open her mouth even a 1 centimeter also. So then she used to manage with the fluids. So now she is 21-year-old. So then what we can do, say as a 3D printing, uh, how it is getting helpful for her to solve this case. So this is what I'm talking about, which you can see this joint got fused. Means the it has become the single member. So it has become integral part of his. By birth, she had that problem. So luckily, you have other side. So luckily, you have other side is say survived side is given as a hint to say try to reconstruct the same geometry on the other side anyway, which we are going to dismantle this. We need to release this fusion of the giant should be released, and it should be say then only she could able to articulate the jaws. And again the job here is to reconstruct this thing here. And this will go in a two-level surgery. So the first level is a distraction osteogenesis procedure, like which we have seen in the previous example, like say cutting the bone and stretching this bone forward, maybe slightly 1 mm, 2 mm, 3 mm, like this, which you can see. So during that transformation of this bone, so which you can see initially, so there was a mismatch here. And once you stretch forward this bone like this, so around 19 to 20 mm, so it has been say aligned. So in this way your say your distractor device, the distractor will be helpful, and then these models will be helpful for designing these devices, then how much length it should be stretched forward, and then those things can be done based on these models that has been taken from the patient. So this is during the surgery where it has been say say it has been say placed this distracted during the transformation, and we so this is the initial stage of the patient, and now you can see it has been matched. So here, so in this way, this is the first level surgery, and the major part is this is the one where we need to say you have this joint which connects your lower jaw, the condyle portion, and the zygomatic arch from this maxilla portion, and you have the fossa where it will go and sit inside. So your condyle will go sit here, the fossa component. These three will become as a unit or a joint. Then we need to say reconstruct this joint. That is the thing. And then you, why this is so complex for a oral maxillofacial surgeon is you have a several nerves which is near to your TMJ joint. So where you have the joint here and you have several nerves here, and we need to have the nerve relieving should be done and all that. Okay, so then it will yeah, this is what exactly I'm talking about. So you have the CT images of the patient and it is being reconstructed, and further we need to say release this joint. Why? Because it has been fused. We need to remove this fusion of this joint, and further we need to say design this joint, and that is through the implant. So we are going to say design this, and this has been say supplemented. So then here what we have done is we took the survived say side dimensions and the form, everything has taken copied on the other side of the jaw, and this is the design of the condyle portion, and this is initially we printed into a polymer based system to check how it is coming, and then further you have the fossa component, and where your condyle will come and sit inside. So this fossa component also, so we have say took the aid of the survived portion dimensions, and the form has been say taken the help here to and this is the design of the fossa, and then further it has been printed in a biocompatible material from 3D printing technology. And this is from the upper jaw where you can see you have the zygomatic arch and you have this fossa component, and this will go to onto the maxilla, that is upper jaw side. And if you see the from the mandibular side, the lower jaw side, so it will come like this, and finally your joint will be in this way. So it has been say exactly mimicked the geometry and the form of the patient, the native patient. It has been retained, and this is what the joint say it consists of. So then this is initially we have checked on a polymer based printer to print these models as well as the implant, and finally it's been printed into a titanium 64 through a metal 3D printing system, and this is what it's going to be, and from the bottom and from the top, so it is getting say fixed. And in order to say avoid the friction, so metal to metal contact, so now it has been say used as the biocompatible polymer as well as the metal has been say used here, and this is the final joint. It is getting say fixed inside the patient during the surgery, and this has been say we have designed an guide also to assist the surgeon to fix the to drill the holes to for the fixation of the implants from the upper jaw side to the lower jaw side, and we have designed the guide and we have supplied them for during the surgery. They have used this guide to fix the um, screws for, and I was very well there inside the surgery, myself and my PhD scholar and my collaborator, Professor Anne Gibson from Australia. And we have here, so once this fusion has been released, so the fusion, so for the past 20 years, she has been surviving in this way without opening the mouth because this got fused. And once this fusion of the joint has been released, now she has opened out a 5 centimeter opening of the mouth, normal opening of the mouth. And ultimately it has been fixed from the say the upper jaw side. uh, this is the one where with the screws it has been fitted, and from the lower jaw side, so this is the one it got fitted. And now we can see she could now be able to open her mouth, normal opening of the mouth, say 5 centimeters, and normal biting and normal chewing has been attained. So then, after 21 years, now she has say have a better societal life. So then, in this way, wherever you have certain long-standing or complex surgeries which they come across, so definitely this is the technology for resolve those kind of complex situations. Normally, they face the surgeons will face during their surgical treatments. And the last case for this presentation is basal osseointegrated implant. So this is an accident case. Then who needs, say, an implant? So why? Because so he lost the 5 teeth. So because of this, um, say, the accident, so he lost the 5 teeth, and along with the bone, the 5 teeth and bone also he got damaged. And this is with the CT scans which we have reconstructed. And now if he is having a certain bone support here, so then you can go the conventional implants that are available from the market. So then they can fix the 4 or 5 implants, but that is not the case here. Why? Because it doesn't have any support to take up that implants to fix that implant. So the then it has forced us to design an indigenous implant or the patient uh, matched or patient specific implant for fitting here. So, and we need to attain the nerve relieving also here. That is another requirement from the surgeon side. We need to attain the nerve relieving also. So this is what I am talking about. So you if you have a support, then you can make use of the 4 or 5 implants, and then you can fix it. But you have hardly the bone support. So then what we have done is, so we have designed a an indigenous implant here. So which it is say getting say designed, and further it has been fabricated, and further it has been tested for the say loads, the maximum load conditions, and say which we e- even tested the fitment of it. So this is what, and which we can see this is a an asymmetric fracture that he happened to be an accident, and then this has become an asymmetric of fracture. So then we need to design the implant as for the patient condition. So then we have designed as for the patient fracture condition, and this is the thing which we can see there is certainly there is a difference in the dimension from one to other side, because this is an asymmetric fracture he went. And then finally it has been printed, and this is the design, actually design and the analysis. And finally we printed, initially we printed with the polymer based printer to check the fitment and how it is getting fitted, so the fitment checking and other aspects. So initially we printed in a polymer based material like PLA on a desktop based printer, just to understand, and giving it to the surgeon to rehearsal or to get some kind of an idea, so what he's going to do during this surgical treatment, and then this is what it's going to be. Then finally we could able to say uh, accommodate 4 teeth even rather than instead of 5 teeth, but it has been went for the 4 teeth, and this has been and this we have printed this metal implant. So in titanium 64, it has been printed on the a powder bed based 3D printing system. So, and this is along with the supports, it has been printed, and then it has been say removed the supports and then performed the sintering, the what you call, you have a certain FDA approvals. Autoclave is the method to sterilize this say implant. So then autoclaving has been done, and as per the FDA say standards and the guidelines, so which we need to ultimately do that say and follow the regulator standards and follow the ethical committee the guidelines, and then which it has been fitted during the surgery, where you can see initially before fitting it and after final fitment of this implant inside the patient mouth. So which you can see this has been printed and it has been implanted. And this case study we have published in one of the prestigious journals in 3D printing area, that is Rapid Prototyping Journal. And if somebody is interested, you can go through this article also for further reading. And finally, we can see you have these 4 teeth, and this is the post operative surgery. So where the image has been taken, so the implant has been um, located in this way, and where you have this 4 teeth has been, so you have, this is a permanent implant, so it will be there forever. We are not going to say remove once again, but it's a permanent implant. It has been, it will be there forever on the backside, and you can see these are the um, say, and the teeth it has been fixed. So in this way, you can make use of this technology for these solving these kind of complex surgeries normally they came across. And then even you can take up certainly some cases, like say you have some abnormal growth of the tumor. So how complex for a surgeon to operate this kind of say tumor cases, abnormal growth of the tumors. So then how they are going to handle this through the conventional methods, but definitely through this medical imaging processing and 3D printing. So they will perform this surgery in a more simpler manner. Normally they do in a conventional or traditional procedure. Normally they come across, and then even the cleft cases, you can find several cleft cases by birth. They have these kind of cases, and then these kind of cleft cases can be solved by using 3D printing technology, with the aid of 3D printing technology. But some head injuries or some accident cases or some trauma cases and some emergency cases, so definitely um, we need to double ensure that whether you are able to say supply these models and on time. Why? Because it is a emergency basis this surgery, but we need to check whether but nowadays you don't have such a problems. In the recent developments are happening, you can even print these models very faster than the previous practice. But though we need to check our facility and we need to check our equipment which you are using it, whether it can be say supplied on time to the surgeon's requirement. Then based on that you can say take up your case, and then accordingly you work on that. And so far we are discussing the 3D printing in the what you call the bone, the tissue, maybe bone and the bone reconstruction and the bone replacement. But it may not be much challenge for those cases which normally you discuss. But if you are targeting to an organ printing, or you are trying to say print an organ, like you have a cardiac ventricles. So if you are targeting these kind of say organs and the tissues, so So, but the procedure remains same. Means the steps, but the material only the difference here. Like say again, you need to start with the MRI scan data of a human heart, and you have a bioprinters or collagens or human heart cells should be taken. Why? Because so in the argon printing, which we need to take the living cells of the one patient, which we need to. So you take the living cells of the human patient, the same patient, the same the living cells will be taken, and you prepare a collagen and prepare the cell ink, or you do cultivate these cells in an incubator, and further it has been added some proteins, nutritions, and then finally you prepare a material. Here purely it's a natural material, and purely it is a living cells of the patient, and then further it has been printed, or further it has been introduced into the patient back. Means where you are targeted, like whether you have taken these cells, living cells from the heart portion, and again you may be repairing or you may be replacing those cells from own living cells of the patient. So it's going to be so like, then what is the state of art of this argon printing? So then the people has already successfully say implanted, or say replaced the blodders. um, Blodder may be a bit simpler than the heart or any other say complex organs. Even the people has already successfully implanted the skin blood vessels, but skin blood vessels may be relatively less complex organs or tissues. But if you target to complex organs like lungs or heart or liver or a kidney, definitely it's going to be very challenging stuff for these people. Say, as we understood, like you extract the cell from the own patient body, and then you combine that with a soluble thing, and within that you are adding some uh, nutritions, and then you are cultivating it in an incubator, and then before it is getting implanted, again you may be testing it against the mechanical properties of the organ as such, the cells it consists of, and then whether it is on par with the native organ. You do use certain bioreactors to do this job, and certainly once it has been passed those tests or those benchmarks or those standards normally attained, but still it is an early stage to have or to expect much standards in this argon printing, saying that hey, these are the standards to go to replace your say heart, or to replace your say lungs, or so it is quite early to discuss. But anyway, so the exciting developments are happening in this direction. So then once you you can expect maybe the entire organ, any complex organ, something like as for the demand, so you could able to supply, maybe you could able to print them through 3D printing technology. These organs may be printed. So, but this is the state of art of this argon printing through additive manufacturing or through a 3D printing technology. So this is the state of art. And let me summarize what I have done for the last 1.5 hours. So we started with the medical scanning technologies like CT, MRI, and we thoroughly discussed how we can import these images, and further it has been reconstructed, and by making use of certain software tools to process this data, and taking the region of interest and organ of interest and tissue of interest from the scanned images, and further it has been grown into reconstructed into virtual models for either a diagnostic purposes. You may use these models. Further, the physical models has been printed through 3D printing technology, and we have seen some of the case studies, which our personal experience I have explained through this pre-planning surgical models is one of the case study applications, and through the other case studies like 5 and 6 case studies, then we have customized designed implant and prosthetics has been done, and even it could be a device can be say fabricated for implantable, that is permanent implantable, or even non-implantable certain areas like the tools, jigs, or templates just for assisting the surgery. You may use this as a device. So then that is also the 3D printing which you can make use of it, and supporting devices for arm braces, knee braces, and any other supporting devices you can done through 3D printing. And of course, tissue engineering, organ printing, bioprinting is all about the state of art. It may be limited as of now to a simpler organs or a simple tissues or simple organs, like say blood vessels or the bladders or skin, has been proven and has been people has been successfully printed those tissues or the organs, the simple organs, but not like a complex organs, which you may be anticipated. I hope maybe other speakers. I am not expert in this organ printing as such, so I have been working in the 3D printing and the medical applications. But definitely, other speakers might have given a lot of insight into the organ printing and how the 3D printing technology is helpful for the organ printing scenario. And before I hand over to the organizers, I would like to acknowledge a few people. So, say we cannot done independently this work. Why? Because it is an interdisciplinary research. It, the the requirement will come from the hospital, and again the end users again, or the hospital people. So then we would like to acknowledge our team or our collaborators from the hospitals, that is oral maxillofacial surgeons from say Panniya Dental Science and Research Center, Hyderabad. So Dr. Shekhar Reddy and Aditya Mohan, for their support towards oral maxillofacial and craniofacial say cases. And and I would like to acknowledge Dr. P. Mahesh, the dental surgeon from Narana Dental College, Nellore, and the financial support from DST and SCRB in terms of the project sanction for the financial support has been highly acknowledged here. And last but not the least, so you might have seen the citations of the papers. So those are the contributions of my UG, PG, and PhD scholars, and of course the PGs from the hospital side for who involved during these 6 cases. In these 6 cases which are presented during this session. So I would like to acknowledge all the people who involved directly or indirectly to complete this work. So I would like to thank them. And we have facilities at NIT Warangal, 3D printing facilities. We have metal 3D printing facility, that is a 3D systems DMP Flex model for metal 3D printing say facility. And we have a couple of Stratasys USA make Dimension Series FDM machine and Mojo FDM machine. And we do have a desktop based printers, Ultimaker 2 Plus, and we do have scanners, AnyScan, SenScan, and we do have a muffle furnace short painting for the post processing of metal 3D printed parts. And we have a dedicated softwares for 3D printing. We have a Mimic software from Materialize, Magix, and Thematic for doing medical image processing as well as designing the implants, and of course operating with the STL files, file problems, and other things. And Catalyst and 3D Expert is for simulation of metal 3D printing processes. So we have these softwares at our institution, and we are running an MTech course in additive manufacturing. So that is the first time in India which we started. We took the initiation, say, and then we started in 2014 onwards. This course has been offered, and these facilities has been extended for the MTech course, and of course BTech course for their dissertation works, and of course PhD people also. It's open for them to do a research on this. Yeah, and I have done from my side, and if you're having say questions, I am very much say excited to answer those questions.